In this video, let's look at some additional problems for deterministic finite state automata. As we've said before, all the problems for deterministic finite state automata and regular expressions and regular languages in general are decidable. We already looked at the acceptance problem for deterministic finite state automata in the previous video. And remember, we had the set A sub DFA to test whether a string W was accepted by a particular deterministic finite state automaton. We also looked at non-deterministic finite state automata, and we also looked at regular expressions. So we were asking, do they accept a particular string W? And so that is the acceptance problem, and we'll use A going forward as a symbol for problems regarding acceptance. Is a string accepted? We can also ask about the emptiness of a language. So we'll use E for that, and we'll use EQ for equality testing. But let's use E for emptiness testing. So the question is the language empty? Okay, is it the set that contains no strings? And in this case, the language we're interested in, E sub DFA, consists of those strings that represent valid deterministic finite state automata, and the question is, does that finite state machine accept any string at all? And we'll use the EQ for equality. Are two languages the same? So for the question of regular languages, we can provide two deterministic finite state automata, A and B, and ask, do they accept the same language? Are they equivalent in the sense that they accept the same language? All of these questions are decidable, but let's look at them a little bit more. Okay, let's look at the emptiness problem for regular languages first. And that problem is described by this language, E sub DFA. And here we're looking at the strings that are valid representations of deterministic finite state automata for which the language that is accepted is empty. In other words, does this deterministic finite state machine accept any string at all? And to show that this is a decidable problem, all we need to do is provide an algorithm to decide it. And the algorithm is really quite straightforward. Given a deterministic finite state automaton, we ask one simple question. Can we go from the initial state to any final state following transitions in the machine? If we can reach a final state from the initial state, then that deterministic machine could generate some string. Okay, if there is a path from the initial state to a final state, then those transitions are labeled with symbols from our alphabet, and they describe some string that this machine will accept. So, is there any final state that is reachable from the initial state? It turns out that this is essentially a graph problem. Okay, a deterministic finite state automaton is a directed graph of states, and so we have to ask whether a path exists. And the algorithm is pretty straightforward, but I'll just go through it here. One approach is, the simplest approach is a marking algorithm. Okay, so we're going to imagine drawing the graph on a piece of paper, the way I've done in the past, with little circles for states and little arrows for the transitions. And we're going to mark each state, potentially, and we can imagine taking a pen and putting a little check mark next to each state that we want to mark. And so what we're going to do is we're going to mark the initial state with a check mark, and then we're going to repeat in a loop this step here, okay? And we're going to repeat it until we can't do any further marking. And what we're going to do is we are going to mark any state where there's a transition to that state from a state that's already marked. So to put this another way, we're going to look at every single transition in turn and ask whether that transition leads from a state that is marked to a state that is not marked. And if so, we're going to mark the state that was not previously marked. And then we're going to keep doing this, keep looking through those transitions until at one point we can go through all the transitions without marking any new states. And then after that, we've marked everything that's reachable. There are no transitions from marked states to unmarked states. So we've marked all the states that are reachable from the initial state. And then all we need to do is check to see whether any of our final states in the machine got marked. Now, we can see whether there's a path in a small graph just by looking at it. So this is a problem we as humans can solve very quickly and easily if the graph is presented visually and is relatively small. But we need an algorithm in case in case we have a graph that's not represented graphically and that is not small. So you can imagine a finite state machine with 10,000 states, and you can imagine a transition function that's specified as a computer file with thousands and thousands and thousands of transitions. In that case, determining whether we can get from the initial state to the final state is much more complex, and we would need to write a computer program to do it. But we can do it, and that computer program will terminate. Now, if you look at an algorithm and you see a repeat statement, and until something, you should immediately get suspicious and think, will this thing terminate? Or will this repeat loop just keep going forever? And we can see that this repeat loop will eventually terminate because it repeats until no new states get marked. So every iteration of this loop has to mark at least one state. And we have finitely many states. So eventually, either every state will get marked or we'll not stop marking things, but we won't keep marking states because we do not have an infinite, inexhaustible supply of states to mark. So eventually, we will not be able to mark any more states, and the loop will terminate. So this problem is decidable. Next, let's look at this question of determining whether two deterministic finite state machines are equivalent. Remember, by equivalent, we mean that the languages that they accept are identical. So this question is decidable. Given two deterministic finite state automata, we can determine whether they accept the same language or not. And so we have to come up with an algorithm. And your first idea might be to say, well, okay, each one of these deterministic finite state machines is a graph, so we can just sort of compare the graphs. And then you might think, well, they might have different state names, so you somehow need to ignore the state names and see whether the graphs are the same or not. You have to be careful. You can get into some problems here without thinking a little bit more accurately about all of this. Here is a deterministic finite state machine, or in part of one, that will accept a sequence of A, B, A, B, A, B, followed by C. And here's another set of states that does the same thing. A, B, immediately followed by C, or maybe A, B, followed by several more A, Bs, followed by C. These two graphs accept the same language, but they're different graphs. So you can't really compare. If you try to compare these two graphs, you'll say, well, they're different. And it's not just because the names of the states are different. So I'm going to next talk about a different way to determine whether the languages are the same or not. And to do that, I want to talk about symmetric difference. So let me define the symmetric difference between two sets, A and B. Okay. In this case, we called our machines A and B up here, and a language is a set, but perhaps I should have called these X and Y down here. But in any case, let me talk about what symmetric difference is. The symmetric difference is anything that's in the set A or it's in the set B, but it's not in both A and B. So it's exactly that area that I've drawn red. And here is a definition in symbols of it. Let's break this apart. A intersected with anything that's not B. So here's A, and anything that's not B is here, okay? So is outside of B, and so this moon right here is A intersected with not B. We're removing the parts of B from A, and we get this little moon shape here. And then likewise, B intersected with not A is this moon over here. This is B, the part of B that's not included in A. And then when we union those, we get the symmetric difference. So what can we say about two languages, A and B, if they're the same? Well, if the two sets are the same, then it's effectively moving these circles until they completely overlap, and everything's white and there is no red. So if A and B are equal, then their symmetric difference will be the empty set. And so we can use that in order to determine whether two languages are equal. How do we do that? Well, we're given two deterministic finite state machines. One accepts the language of A and one accepts the language of B. So we know how to manipulate deterministic finite state machines. We know how, for example, given a finite state machine, to modify the machine so it accepts the complement language. Remember, we just switched the accepting states to non-accepting states, and the non-accepting states we switch to accepting states. So we flip the states from accepting to non-accepting. Likewise, if we want to do union or intersection, we know how to build finite state machines that will do that. So, in summary, we can build a new deterministic finite state machine, C, that will accept the symmetric difference of A and B. And then we use the Turing machine from the previous theorem. Remember, that was the one that detects empty languages. And we test to see whether the symmetric difference is empty. So, just to recap, we want to construct a Turing machine, and it has as input two deterministic finite state automata. Out of those, we construct a new deterministic finite state automaton, which we'll call C, to accept the symmetric difference of whatever languages A and B accepted. And then we use the Turing machine from the previous theorem to test whether C accepts the empty language or whether it accepts a language with some strings in it. And if C accepts the empty language, it can only be because languages A and B are the same, and that machines A and B are accepting the same language, so we should accept. And if C is the empty language, we accept, and if it's not the empty language, we reject.